Honors Geometry, section 13.2 notes. Chord theorems. Just kidding, chord theorems. Theorem 13.2. Two chords. Remember, a chord is a segment whose endpoints are on the circle. So, chord, 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 chord. Two chords are congruent, same size, if and only if their corresponding arcs are congruent. If and only if means we can read it forwards or backwards. So, two chords are congruent. Let's read this in one way. If two chords are congruent, which is the first picture shows, then their corresponding arcs are congruent. So that means this arc and this arc have to be congruent. Reading it backwards, two arcs are congruent. Let me start over. If two arcs are congruent, looking at this picture, then their corresponding chords have to be congruent. Theorem 13.4. Why did it skip from 2 to 4? Because this if and only if means it's two theorems rolled into one. 13.4. If a radius, or diameter, is perpendicular to a chord, then the radius bisects the chord and the arc. So notice in this picture that this diameter is perpendicular to this chord. When that happens, it will cut this in half, and it cuts this in half as well. Theorem 13.5. If a segment, or diameter, is the perpendicular bisector of a chord, then the segment goes through the center. I think this shouldn't be here. If a segment is perpendicular bisector of a chord, and this picture shows segment EB is perpendicular in the bisector, then the segment goes through the center. This is the converse to this up here. So this tells us for certain that the center of this circle has to be on this segment. Two chords are equidistant from the center if and only if the chords are congruent. So in this first picture, we could say these two chords are the same distance from the center, because it shows that. The conclusion that we can make is that these two chords have to be the same length. Since this is perpendicular, it makes each of these halves identical. Saying this backwards, if two chords are the same length, and I don't like where that mark is, let's say that mark is here, then that must mean these two chords are the same length from the center. And when that happens, that's going to hit at a perpendicular. Well, let's see if we can put this into practice. Those theorems are a little aloof. Find the measure of arc CF. That's this fellow right here. Remember that if we go all the way around the circle, that's 360 degrees. Recall also the theorem that we just had, which would be the first theorem. Two chords are congruent if and only if their corresponding arcs are congruent. So these two chords are equal, they're congruent, which means their corresponding arcs have to be the same. It's 106. Now going around this circle, we got x plus 106 plus 106 plus 33 has to be 360. X plus 106 plus 106 plus 33 has to be all the way around the circle, which is 360. X plus 245 is 360, which makes x 115. It says find a measure of arc CF, 115. Number 2. Find the measure of arc CE. Since these chords are all the same, their corresponding arcs have to be the same. So we can call all these x. So 3x plus 108 is all the way around the circle, which is 360 degrees, which means 3x is 252, which means x is 84. To answer the question, the measure of arc CE is 84 degrees. Number 3, this gets a little tricky. Work with me here. This arc is made up of 2 dashes and 1 dash. This arc is made up of 2 dashes and 1 dash, which must mean that these arcs are the same. If those are the same, then that makes this chord and this chord the same. That's the first theorem we had today. Which means if this blue one is 10 plus 2, that must mean the purple one's also 10 plus 2, which makes x 10. Hopefully that makes sense. Number 4, picture shows that this is a right triangle. Picture shows that this segment is 5, and this one also has 2 dashes, so it's 5. That makes this a right triangle. And if you recognize this is a Pythagorean triple, this is a 5, 12, 13, which makes this here 12. And if that's 12, and this other little part down here is 2, that makes the diameter 14. If the diameter is 14, then the radius, which is what x is, has to be half of 14. That makes the radius 7. This is centimeters, so the radius is 7 centimeters. Find x, 2 decimal places. Well, one of the theorems that we had on the front is that if a segment hits a chord at a perpendicular, then it cuts the segment in half. It sets the chord, cuts the chord in half. So if 10's the whole thing, each of these have to be 5. You might be thinking, hey, this is a 3, 4, 5 right triangle. Well, it couldn't be, because then you're saying the 3 is the hypotenuse. 5 is supposed to be the hypotenuse in a 3, 4, 5. So we could figure this out using the Pythagorean theorem. Let's say x was the 5 and y was the 4, and we don't know what r is. Let's call that x. It's 25 plus 16 equals x squared. Be 41 is x squared. So x is the square root of 41 plus or minus. Excuse me. Let's say that's the positive version of 41. Using a calculator, we get 6.40 to 2 decimal places. And this is centimeters, so I should put a little centimeters on there. Sweet. Number 6. Now, this problem in its current state feels impossible. But let me do something for you here. Let's take this radius. I can put this radius any place I want. Where's the best place to put it? Best place to put it is right here. We got a right triangle. Specifically, we have a Pythagorean triple. This is the 3, 4, 5 right triangle. X is 5 centimeters. Number 7. Well, this is easy if you know your theorems. Since this segment intersects this chord at a 90, that makes this side and this side the same. It makes this whole thing 6.5 times 2, which is 13. If you know your theorems, this chord is the same distance away from the center as this other chord, which means those chords are the same length, which makes x also 13 centimeters. Boom. Find the value of x here. This is 90. That makes the central angle 90, this being the central angle. If that's 90, these two have to be this, well, these two have to be the same, these segments, these radii, because they're radii, they're always the same. That makes this an isosceles triangle. And an isosceles triangle, if you have an altitude, which is what this little fella is, it's also an angle bisector, which makes each of these 45, which makes this 45, 45, 90. Now, if you know your 45, 45, 90s, and boy, do I hope you do, because it's super important, especially when you get into pre-calc. This is the short leg times the square root of 2, which is going to make the short leg 12, and x is that short leg. So x is, oh, not centimeters, there's no units, x is 12. Number 9, construct a circle that contains the given points. So that means that there's some circle here that when we draw it, B, C, and A are on the circle. Now here's how this works. You want to draw a chord from B to C and A to C. Or you could do it from, B to A and A to C. You want to draw two chords. Now, one of the theorems that we had back here, which would be Theorem 13.5, if a segment is on the perpendicular bisector, no. Yeah. If a segment is on the perpendicular bisector of the chord, then the segment goes through the center. So you want to construct the perpendicular bisector of each of these segments. Now to do that, I don't have a compass here to show you, but if you put the pointy part here at B, and you put the pencil at C, and you draw and measure that distance, I guess we don't have to do that. We have to set our protractor, our compass, so that it's half the distance. Make a mark, and then you move it over here. You make a mark, and then from there, you draw an arc that intersects above and below, and then you connect those. Let's see, 1, 2, 3, 4, 5, 6. You're going to end up with a segment that's kind of like this. Makes this the perpendicular bisector. If you do the same thing from AC, if you construct the perpendicular bisector, it will look something like this. Those two perpendicular bisectors will always intersect at the center because they both contain the center. So that means that the circle that we're drawing, it's going to be a little something like this. Now it's unfortunate that the center of the circle is not at a place where the ordered pairs are integers, but it is, as they say, what it is. So it's right in that location, which is about 2 to 4 point something, I don't know. It says construct the circle. Had you did it to scale using a compass, this would have worked out perfectly. I don't have a compass here, I'm just doing it freehand, so mine did not work out so perfectly. That concludes the notes for section 12.2.